Hey guys, welcome back. We're going to do a little section on transformers here, single phase transformers. And this is the last topic we're going to cover together before the test. And so let's just talk about transformers real quick, then we'll do a bunch of math, see if we can figure out, what's going on with a transformer. I've got some notes started here for you, and, we'll talk about them in a second here, okay? So, what is a transformer? Well, a transformer is a magnetic machine, really, which is used primarily to change the voltage. And they only work in AC, and they basically work by, I've got two, examples of transformer drawings here. This is the one you're going to see, on a schematic here. It's got two windings. This one's the primary winding. Here's the secondary winding. And I've got the equivalent kind of a drawing here, but maybe a little bit more as to what's going on here. I've got the primary winding here. This is iron, guys, and that's what these two lines represent. Here's the secondary winding. Now, before we get too carried away, let's talk about the why this is the primary winding and why this is the secondary winding. And the definition of the primary winding, guys, is the winding that's connected to the source. Okay, so this is going to be your source voltage here. I don't know what it is, but it's connected to some sort of AC source here. And the secondary winding is always the one that's connected to the load. And I'm going to draw like a resistor here or something like that, but it could be a panel, lighting panel or something like that. Could be anything, right? And so secondary, guys, always the winding that's connected to the load. Primary, always the winding that's connected to the source. There's three different kind of things that you can do with the transformer. One is you could have a step-up transformer, and a step-up transformer is a transformer that you're trying to increase the voltage. Okay, so maybe you'd have 208 here and you need 600, and so you're going to use a step-up transformer to go from 208 to 600 volts. Step-down transformer is a transformer that decreases the voltage. So, for example, the exact opposite. Let's say I had 240 volts here, and I needed 24 volts for something. So 240 volt primary, 24 volt secondary. And it doesn't matter if it's step up or step down. Okay, even if it's a step up transformer and you're going 240 to 600, the 240 volt or the lower voltage would be the primary because it's the one that's connected to the source. And the 600 volts would be the secondary because it's connected to the load. Okay, guys? There's another kind of transformer that you can experience, and that is what's known as an isolation transformer, and it just doesn't change the voltage at all. So an example of an isolation transformer is one that would be 120 volts here and 120 volts there. And in the case of an isolation transformer, these two, obviously, you're using it to change the voltage. The isolation transformer, you're not using it to change the voltage. You're using it to isolate one circuit from another because there's no electrical connection between these two windings, the primary and the secondary. Okay, they are isolated from one another. There's a magnetic, interaction that's going on there. Here you can see it there. Electrically, no connection between the primary and the secondary. So if you're doing isolation, you're not changing the voltage. You're trying to isolate those two circuits from one another electrically. All right, and that gets done for various reasons. But mostly it's to reduce electrical noise. So if you had a bunch of electrical noise over here that your load wouldn't be able to tolerate, you could use an isolation transformer and it would, knock off some of that noisy electrical from the primary side. By the time it gets to the secondary, it would be cleaned up a bit. All right, guys? So that's an isolation transformer, and it's used in a case where you don't want to change the voltage, but you want to clean up your source voltage a little bit. Now, the way transformers work, guys, is basically if you look at this one right here, you connect an AC source here. This is going to be, magnetically flipping back and forth. And the voltage that's inducing this magnetic field into this thing here, which is flipping back and forth, actually induces, induces a voltage into the other winding. So this one is causing a magnetic field to flip back and forth in this iron, and then the iron magnetic flux that's, expanding and contracting is actually inducing a voltage into the secondary winding. So even though there's no electrical connection, there is, a transfer of energy from the primary to the secondary magnetically. All right, guys? Now, the question becomes, like, how do I change the voltage? And actually the way they change the voltage, well, if you look at this here, guys, let's say, just for fun, that this was 240 volts, okay, guys? And the way they change the voltage is they change the number of turns with respect, from one winding with respect to the other. So let's just say for fun that this is 240 volts, and this particular winding is 480 turns of wire. If it's 480 turns of wire and it's 240 volts, then the amount of voltage that's dropping on each turn is going to be a half a volt. All right? Because, every one of these 480 turns is going to drop a half a volt here. And if this thing is dropping a half a volt per turn, the secondary winding will have a half a volt per turn induced into it. And so in order to change the voltage, I just put more or less turns in the secondary winding. So if I wanted to reduce this voltage down to 120 volts, I would just put 240 turns of wire on the secondary. And, I can figure out the volts per turn here, guys. The volts per turn is going to be equal to the voltage, over the number of turns. And we'll call that N. And since the voltage is 240 and the number of turns is 480, then the volts per turn is equal to 0.5. Okay, guys? Volts per turn. Ugh, super ugly there. All right, guys? Sorry about that. And since this is dropping 0.5 volts per turn, the secondary winding is going to actually increase or, be also 0.5 volts per turn. And so for this particular transformer, if I want to figure out, the voltage on the secondary side, it's the same formula. The volts per turn, it's going to be the voltage over the number of turns. And I know the number of turns and I know the volts per turn. So if I transpose this, the volts is going to be the volts per turn times the number of turns. All right, guys? And so it's going to be the 0.5 volts per turn that I have on the primary. And I'm going to multiply that by the 240 turns, and I'm going to get 120 volts. All right, guys? And so that voltage, that formula that I just applied here to figure out what was going on with this circuit is this one right here. Actually, I should add one right up here, the volts per turn, It's going to be equal to the voltage over the number of turns, okay? And we're just going to call that number of turns N. All right, guys? And the volts per turn on the primary will always equal the volts per turn on the secondary. All right, guys? So forget about these formulas for right now. Let's see if we can figure out what's going on with this formula on this little example right here. I've got another example here that I want to do with you guys here. I got a transformer that is 600 volts on the primary side, guys, and then on the secondary side, I'm not sure what the voltage is. We're going to see if we can calculate the voltage by calculating the volts per turn here, and then calculating the, then we'll know the volts per turn here, and we're going to calculate the low voltage that way. But then I'm going to show you another way to calculate the low voltage using not the volts per turn formula, guys, okay, but by calculating the ratio and then using the ratio formula, okay, guys? And so let's do it the old-fashioned way here for a second here. We'll calculate the volts per turn on the primary side, guys. And the volts per turn on this primary side is going to be volts per turn. It's going to be the voltage on the primary side times the number of turns on the primary side. Looks like it's 600 over 300, guys. And so it looks like it's going to be 2 volts per turn. Okay, guys? And since it's 2 volts per turn here, it's going to be 2 volts per turn here. And since the volts per turn is equal to the voltage, over the number of turns, so the volts per turn is this voltage over this number of turns, it's also this voltage over this number of turns. So we can use the same formula for the primary and the secondary. There's the secondary formula, we've just figured out the volts per turn. We know how many turns there are, so we're going to solve for V. And that means the voltage on the secondary side, guys, is going to be the volts per turn times the number of turns. Okay, guys? And voltage on the secondary is going to be 2 volts per turn, okay, times 125 turns. So it looks like it's going to be 250 volts, okay, guys? And that'll work to calculate the secondary voltage. But there's another way. And the other way is to calculate the ratio of the transformer using, you know, whatever means necessary, okay, guys? And in this case, since we have the turns on the primary and the turns on the secondary, we're going to calculate the ratio of this transformer. The ratio of this and every transformer is always going to be the number of turns on the primary, on the high voltage side, I should say, over the number of turns on the secondary or on the low voltage side. I keep interchanging those, but in this case, it's the number of turns on the primary over the number of turns on the secondary. It is actually the number of turns on the high voltage side over the number of turns on the low voltage side. So in this case, the ratio of this transformer, guys, it's called the turns ratio, by the way. It's going to be 300 over 125. And so if I take that 300 and divide it by 125, I get a ratio of 2.4 to 1. And the nice thing about the ratio is it applies to everything in the whole transformer, okay, guys? Because look at formulas for ratio. There's 3 of them. One has the high number of turns on the high voltage over the number of turns on the low voltage. It's also equal to the voltage on the high over the voltage on the low. It's also equal to the current on the low over the current on the high, and we'll talk about this one last. We're working on this one right now. We've used this one to calculate the ratio, but now that I know the ratio, I'm going to see if I can use the ratio to calculate the low voltage. Okay, guys, so this transformer, 2.4 to 1, and I know that the ratio, guys, is also EH over EX, which means EX is equal to EH, if I transpose that over the ratio, guys, and EH is 600 and the ratio is 2.4. Okay, guys, so if I go 600 divided by 2.4 equals, I get 250 volts, okay, guys, on the secondary. So what I'm trying to show you here is that if you can calculate the ratio of the transformer, guys, you can calculate the voltages on the transformer as well. And if, you know, I'd highly recommend that you calculate the ratio of the transformer, you know, right away. Because as soon as you know the ratio, you've got 3 formulas, okay, that allow you to calculate everything about the transformer. Now that we've done that, let's talk about current for a second here, guys. So we've just decided that this is 250 volts, guys, on the secondary side. 250 volts, all right? We've calculated it twice in 2 different ways. But I'm going to walk over here and I'm going to notice that the current here is 20 amps, okay? And this is going to be IX, okay? It is the current on the low voltage side, okay, guys? And it's 20 amps. And, you know, if I have a transformer, guys, and the voltage is 600 to 250, then the current on the secondary side is going to be higher than the current on the primary side. Well, and that's because the VA on this side is equal to the VA on that side, and we'll talk about that in a minute. But what I want to do is look at this formula right here, where the ratio is the current on the secondary side, or on the low voltage side, over the current on the high voltage side. And so if I know that the current here is 20 amps, I can calculate the current here, which will be IH. And to do it, I'm going to use another ratio formula. The ratio for every transformer is always going to be IX, guys, over IH. Now, I know the ratio, and I've given you IX, what we're going to do is transpose this formula and solve for Ix. And in this case, Ix, guys, is going to be IH times the ratio. Okay, that's how that transposes. And I already know that IH, whoops, I'm solving for the wrong one. I already know Ix, okay? IH, guys, is going to be Ix over the ratio. Sorry about that. Okay, I was solving for, Ix, but I already know Ix. Okay, I need IH. In this case, IH is going to be Ix, which is 20, over the ratio, which is 2.4. Divided by 2.4, the ratio. According to this, it is 8.333 amps. All right, guys? So we just calculated this as being 8.333 amps. Now, I want you to notice that the high voltage has the lower current and the lower voltage has the higher current. And that's because of this formula right here, which I did not write down yet, but I'm going to right now. And that has to do with the VA of the transformer. The VA on the primary, guys, is going to be equal to the VA on the secondary. And that's because all transformers, they change the voltage, guys, when it goes across here, but it does not change the power. The power in the circuit is going to be determined by this load. If this thing is 1,000 watts, then this is going to be 1,000 VA, and this is going to be 1,000 VA as well. And so the amount of power that goes into this transformer, at least in a perfect world, okay, guys, and we don't live in a perfect world, there are some losses, but in transformer, in theory, we can ignore all the losses, okay? So if this is 1,000 watts here, then this transformer is going to be supplying 1,000 VA to it. The primary is also going to be running at 1,000 VA, and there's going to be a total of 1,000, watts going in and going out, okay? Because this thing isn't changing the power, it's changing the voltage and the current, okay, guys? So if I actually apply that formula, I can calculate the VA of this thing on the secondary. It should equal the VA of this thing on the primary. And don't worry, guys, we're going to have another video, and I'm going to do another one. We're going to see if we can calculate all the things, okay, guys? And, we'll try our homework, okay, guys? So according to my rules here, guys, the VA on the primary should be equal to the VA on the secondary. Okay, so let's calculate in both here. And the VA on the secondary is going to be the voltage on the secondary times the current on the secondary, guys. So it's going to be 250 times 20. Let's see what that is. 250 times 20. Okay, according to this, it's 5,000 volt amps. All right, guys. And just for fun, we're going to calculate the VA on the primary. It's going to be, the voltage on the primary times the current on the primary. So it should be 600 times 8.333. Okay, guys. And so here we go. 600 times 8.333. Yes, 5,000 volt amps. All right, guys. So horrible. All right, guys. What do you need to know about transformers? Well, you need to know that the volts per turn on the primary is going to equal the volts per turn on the secondary. That the ratio is going to be the high voltage turns over the low voltage turns. It's also going to be the high voltage over the low voltage, guys. And it's also going to be the high current, which is why we call it Ix. The current on the low voltage side is going to be the higher current over the lower current, which is why we label it IH, okay? It is the current on the low voltage side over the current on the high voltage side, all right? So high over low, and high current over low current, okay, guys? And those formulas, together with the VA formula, and maybe these two, will allow you to calculate everything you want to calculate about a transformer. All right, guys? So stick around and we'll do another example.